Hello everyone, welcome back to the course Power Plant Engineering. In the earlier lectures, we have started our discussion with the classification of nuclear reactors. Classification of the nuclear reactors is based on different parameters like fuel used, that is the type of fuel used, then the type of coolant used, then the moderator or neutrons flux spectrum. So depending on this, we have some commercial sort of types of the nuclear reactors. The listing or the names of those nuclear reactors is on the screen. The first is the boiling water reactor, second pressurized water reactor, then pressurized heavy water reactor. So these three we have seen in the earlier lectures. Now in this we will discuss about high temperature gas cooled reactor and the liquid metal fast breeder reactors. So as it has been discussed, the nuclear reactors is the main component of the nuclear power plants, where in the nuclear fusion or nuclear chain reaction, energy is released by the nuclear fuels, and that energy has been utilized to convert the water into the steam. That steam ultimately drives the turbines, and turbines drives the synchronous generator, which will produce the electrical energy. Let's proceed for the high temperature gas cooled reactor. First, we will see a liquid metal tank feeder reactor. A fast breeder reactors are designed to create or breed new fissile material while producing useful electrical power. Most produces fissile plutonium from the fertile uranium-238. The fuel rods in the core region thus contains a mixture of fissile plutonium-239 and uranium-238. The active core regain its surrounding or surrounded by a blanket of fertile uranium-238. This blanket region captures neutrons that would otherwise be lost through the leakage, thus producing additional fissile material. So the schematic diagram of liquid metal tank feeder reactor is as shown in the figure. This contains three loops or circuits. First is the primary circuit, second is the intermediate circuit or loop or secondary circuit, and third is the working fluid or steam circuit. The high concentration of fissile fuel and the absence of moderator makes the core of the fast reactor smaller than a thermal reactor of the same power. With a high power density, thin fuel pins are used to minimize a temperature drop through the fuel. A coolant with excellent heat transfer properties is required to minimize the temperature drop from the fuel surface to the coolant, and also it must be non-moderating. This rules out the water, and the best coolant for fast reactor are liquid metals such as sodium. Liquid metals have the additional advantage that their boiling point are at atmospheric pressure is very high. So most of them are used unpressurized in a reactor. Sodium is the most common coolant for the fast reactors. So here in the first, that is primary cycle or primary loop or primary circuit, we can see the energy has been exchanged with the help of a coolant. For example, a sodium is most common coolant, as earlier it has been discussed. So with the help of that coolant, the energy is transferred from the reactor to the primary circuit. Once again, that heat is been exchanged with the help of secondary circuit or intermediate loop with the help of coolant. And finally, the heat is been extracted from the coolant in the third cycle, which will be supplied to the turbine. So this liquid metal tank feeder reactor consists three loops, and in different loops at different level heat is been exchanged so that to maximize the efficiency of the heat exchange. Therefore, we will get a maximum extraction of the temperature from the coolant to the water, by which we can have a pressurized high heated steam which we can enter into the turbine to drive the generator. There are two primary loop designs. One is pull type system and other is the loop type system. In the pull type system, the reactor core, primary pumps and intermediate heat exchangers are all placed in a large pool of liquid sodium contained in the reactor vessel. The liquid sodium is discharged from the intermediate heat exchanger to the pool. It is then pumped upward through the core and re-enters the heat exchangers. In the other type, that is in the pool type system or design of liquid metal tank feeder reactor, the intermediate heat exchanger is located outside the reactor vessel. The pool type of configuration is widely used in the European and American uh, countries. The next is the heavy water reactor. The very low neutron captures cross section of the heavy water makes it an excellent moderator and coolant, and permits the use of natural uranium, that is 0.7% of uranium-235 as a fuel. The reactors of this type have a good neutron economy, resulting in good breeding ratios, high fuel burnup, and the reduction in the fuel cost. The disadvantage of heavy water are its very high cost and, like water, its critical temperature limitations. Heavy water moderated and cooled reactors have been extensively developed in the Canada, and from this basis the nuclear power program in that country. They are called CANDU PHW, that is Canadian deuterium uranium pressurized heavy water. The CANDU reactors have several features that distinguishes them from the other types. The moderator is contained in a cylindrical steel vessel called the calandria, which a large number of zircaloy tubes through its parallel to its axis, which is a horizontal as shown in the schematic diagram of the heavy water reactor. The active core region is approximately 6 meter high with a diameter of 7 to 8 meters. The D2O coolant enters the regular array of pressure tubes at 260 degrees Celsius and 110 bars, which flows through the fuel elements and leaves the pressure tubes at 320 degrees Celsius, and net efficiency is about 29%. Like PWR, that is pressurized water reactor, there is no bulk boiling of coolant. The heavy water coolant pressure in the reactor is 88.3 bar, and the inlet and outlet temperature are 250 degrees Celsius and 290 degrees Celsius respectively. The heat exchangers steam is generated at 41 bars pressure and 251 degrees Celsius. The thermal power of each reactor is 1744 megawatts, and the net electrical output is 515 megawatt, giving a thermal efficiency of around 30%, that is 29.5%. The calandria contains up to 380 horizontal pressure tubes called calandria tubes, which are welded to the tube sheets at each end of the vessel. The moderated temperature is maintained about 70 degrees Celsius and low pressure to reduce heavy water losses. The fuel assembly contains 37 fuel rods as shown in the schematic. Each rod contains natural uranium dioxide UO2 fuel pellets with 0.38 Zecloy cladding. Each rod bundle is about 0.1 meter in the diameter and 0.5 meter long. In the schematic of heavy water reactor, there are different sections and different parts in the heavy water reactor. First is the calandria. This is the actual part of the heavy water reactor. It contains horizontal pressure tubes. These are the horizontal pressure tubes which are welded at the tube sheets at each end of the vessel. The moderator temperature is maintained at about 70 degrees Celsius. Then the part comes the pressure tubes. Here we have 4 pressure tubes. Then heat exchangers. These are the heat exchangers where heat is exchanged from the coolant to the heavy water. Afterwards, moderator and cooling circuit. So this is moderator and cooling circuit, and these are the control rods. So generated steam is at 41 bar 251 degrees Celsius is entered to the high pressure part of the turbine. After that, it will be entered into the low pressure part of the turbine, and then it will once again taken back for the condensation and further utilization of the available temperature in the steam. So this will drive a generator of 515 megawatts and generate the electricity. Let's move ahead about the India's nuclear power program. From the several reactor types available, India has selected pressurized heavy water reactors, that is PHWR, because of several inherent advantages. A PHWR uses natural uranium as fuel with heavy water as a moderator and coolant. The natural uranium being easily available in the India, which helps to cut heavy instruments for enriched uranium, the import of which is very difficult due to restrictive international trade practices. Besides, the PHWR core containing natural uranium is safer with its lesser radioactivity and has on-power refueling facility. On-power refueling facility. Due to its excellent neutron economy, the PHWR has a greater yield of plutonium. India has planned 3 stages program to benefit from the nuclear power or nuclear energy. In the first stage, PHWRs uses natural uranium, that is pressurized heavy water reactors uses natural uranium fuel to produce electricity and plutonium fuel with the 96% unused uranium, that is uranium 238. In the second stage, the use of fast breeder reactor with plutonium as a fuel will generate electricity and more plutonium from uranium 238 kept as a blanket. It will also produce uranium 233 fuel from the thorium which used as a blanket material. And in the final stage, that is third stage, uranium 233 will be used as a fuel and thorium as a blanket, producing more uranium 233 fuel than the fuel consumed in the fast and thermal reactors. India's nuclear power program is been designed and governed by the Power Corporation of India Limited. Since the resources of fossil fuel are fast depleting, India have to depend more on nuclear power. Besides, it is economical to regret to cost of the generation of the electricity. An optimal mix of thermal, hydel and nuclear sources is required to help India to achieve self-sufficiency in the power generation for years to come. Now let's see the operational nuclear plants in India. The first column is name of the power station or the location. The second is the operator. So almost all nuclear power stations have been governed by the NPCIL, Nuclear Power Corporation India Limited. They are located in different states of the India. Let's see first the Kaiga, which has been operated by Nuclear Power Corporation India Limited, which is situated in the Karnataka. And the type of reactor has been placed in this Kaiga power station, nuclear power station, is pressurized heavy water reactor. It is having 4 units. One is of 220 megawatts. So total capacity of the Kaiga unit is 880 megawatts. Then Kakrapur in the Gujarat, which uses a pressurized heavy water reactor containing 2 units, each of having 220 megawatts. So total capacity of the Kakrapur unit is 440 megawatts. Then Kudankulam, which is located in the Tamil Nadu, which uses water or VVER 1000, a nuclear power reactor having 2 units. One is of 1000, so total capacity is 2000 megawatts. Then Madras Kalpakam, which is governed by Nuclear Power Corporation of India, located in the Tamil Nadu, which uses a pressurized heavy water reactor having 2 units and total capacity is 440 megawatts. In Narora, Uttar Pradesh, the pressurized heavy water reactor has been used in the nuclear power plant having 2 units and total capacity is 440 watts. In the Rajasthan, the 4 units as well as further 2 units, so total 6 unit has been run. So one is having 100 megawatt, one is having 200 megawatt, and 4 are having 220 megawatts. So total capacity of the plant in the Rajasthan is 1080 megawatts. And in Tarapur, Maharashtra, boiling water BWR reactor and PSWR reactor has been used. The BWR reactor having capacity of 160 megawatts and containing 2 units of the same, and PSWR 540 megawatts units each capacity and having 2 units. So total capacity in the Tarapur nuclear power plant, which is located in the Maharashtra, is having 1400 megawatts. So biggest in India, we have Kudankulam in Tamil Nadu power plant, which is of 2000 megawatts. So in the upcoming years, there is a huge demand in the scope to the nuclear power in India, as looking out the growing demands of the industry and the different applications. So this is all about the nuclear power plant. Thank you.